These are the slides that I normally start the unit with, but they weren't done, because normally I just like have a paper and I like write everything out, but I didn't like doing that, so I made slides. And it took longer to make the slides than I thought, so now we can do it. As a quick note, so we're going to do slides today. I am not going to give you the assignment for this lesson yet. We'll just do this and then call it good. Tomorrow's homecoming, so we'll just hang out. We'll have our quiz, right? Got our quiz, you need to vote on the first 10 elements. Monday, I'm going to be gone. I'm going out of town this weekend, so I will be gone. So I will have the worksheet for this lesson for you on Monday. We'll go from there. So just so you know what's happening. Boom, slides. What?
I don't like this stuff.
You don't like this topic?
No, because it's all just a bunch of white men.
White men? You're not wrong.
And the white men are all have German or Danish names.
Actually, most of the guys today are going to be British. So, arguably the most powerful empire of all time. So, when you're powerful, you get to do science. That's how that works. And you get to write the history books. Anyway, okay, history of atomic theory. So, we've already talked about some of what we know about atoms today. They have a nucleus, protons, neutrons, electrons, energy levels. They move around in predictable paths, all that good stuff. I want to go through the history of how we came to know this. Okay, so obviously you could take like whole classes about this, but I'm just going to kind of give you a brief overview of it, just so we have an understanding of where this has come from, and also kind of tells us a little bit about how science works and how we do it. Okay, so we're going to go all the way back to the beginning of atoms. Anyone know when atoms were discovered? Is that a recent discovery, or like does this go back thousands of years? Where do we think we're starting?
It does not go back thousands of years.
It doesn't go back thousands of years, yeah. So it's actually kind of a trick question, because the idea that atoms might exist, the idea of atoms does go back thousands of years, okay? With this guy, he's so old you can only paint him, there's no pictures of him. Okay, his name's Democritus. He was not really a scientist as much as a philosopher. And one of the things he wrote about, okay, I don't think this was his entire life's work, but one of the things he wrote about is the idea that atoms might exist, okay? And this is just kind of a logical thought exercise more so than an experiment he did. He did not do any experiments, okay? But he's the one who wrote down this idea that atoms might exist. And the logic is basically, well, you can take an object and you can cut it in half and make it smaller. You can cut that half in half and make it smaller. You can keep cutting things in half. What seems more logical? Do you eventually get to a point where you can't cut it in half anymore, or can you cut things infinitely in half forever and you can go infinitely small? That's kind of the question. And you can probably just debate both sides, because you can't do an experiment at this point in history, right? Or before zero. And so he suggested the idea that you probably get to some particle that you can't cut anymore. Okay, so this is where this idea of an atom comes from. The Greek word atomos means uncuttable. So this is kind of the history of the word atom, and it's called an uncuttable. I guess nowadays, technically, you can break atoms into pieces, and some of them do it on their own, but the original idea was that, well, it's probably some fundamental particle that you can't get smaller than, and so it was kind of on track there. And so part of the idea is that atoms, he believed that atoms were uncreated, so they've been around forever. There's an infinite number of them because we assume the universe is infinite in size, and that they're eternal. They never get destroyed, they were never created, they never grow anywhere. Okay? Not entirely true now that we know today, but This is kind of the starting point, just where we're coming from, and then we'll build from there. Okay, so that's Democritus. So the only thing I really want you to know from here is that Democritus is associated with the beginnings of this word. It's kind of the idea here. And then that word has the idea of uncuttable related to it. Cool. Okay. Fast forward. How many years? I can't remember. 1,700 years. Okay. So, anyone know this guy? Guess what country he's from? Not Britain. Britain's enemy.
Germany,
No, their enemy. Their arch enemy.
France.
France. Yeah, he's French. This is Antoine Lavoisier. Maybe those of you in French class could have demonstrate a better accent than me.
No.
Okay. I wasn't looking at Daniel. I don't know who else here takes French. But yes, it's not Lavoisier, it's Lavoisier. Okay, so you can at least say it that way. He is very significant in the world of chemistry. But on our way to getting evidence for atoms, he is one of the reasons we believe in the law of conservation of matter today. He did not come up with this law, but give me like 30 minutes.
Okay.
You're good. Trying to get snacks. He didn't come up with the law of conservation, but notice what I said here, verified it. So he is famous for doing very, 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 very precise measurements with mass. And so at this time, he obviously, again, in order to have cutting edge technology, you need money. And so someone who's in the upper class of a country is going to have the money to do that. And so that's just kind of how that works. Okay. So law of conservation of matter. Do we know this law? I'm hoping yes. What's the idea here? Matter cannot be created or destroyed, just changes forms. Does that sound right to the rest of us? Some of us think so? Yeah, I'd say so. Since we're talking about atoms, I'm going to use the word atoms. Atoms cannot be created or destroyed in a chemical reaction. So again, we have to kind of be a little more specific because, I don't know, if you put an atom in a particle accelerator and you break it into two atoms, maybe you destroyed an atom even though the parts are still there. It gets, you can kind of nitpick. So we're just going to say they cannot be created or destroyed in a chemical reaction. In other words, the total mass stays constant. And so that's kind of what his work in this area was about, is if I measure the mass of all of my starting chemicals and then I do a reaction and measure the mass of what I end up with after the reaction, the total mass is the same. And so the assumption is, okay, well, the atoms probably didn't go anywhere, they just rearranged themselves somehow. So this is not really proof that atoms exist. They were just kind of assumed to exist at this point. But it is kind of leaning that direction of like, okay, well, if atoms exist, it would make sense that they're just being rearranged in a chemical reaction instead of, you know, like creating a new chemical from nothing. It's just, oh, it came from my starting materials. Okay, so that's Lavoisier. Okay, so he's famous for helping verify this law. Okay, so this law was already around, but he helped verify it with experiments. Okay, so we got that. Moving on. Now we are going to Britain. I think. No, is this Proust? Joseph Proust. I think he's British. Also French. Dang it. I lose track. Also French. Okay, this is copper carbonate hydroxide. You don't need to know that, but fun fact, that's how you say that, copper carbonate hydroxide. Okay, again, doing more experiments, doing more chemical reactions, we're getting evidence that atoms exist. It's, okay, at this point, okay. He realized that there's a pattern, and this pattern has 0 exceptions. A pattern with 0 exceptions is called a scientific law, right? So he did several experiments and realized that when you have a certain compound, so say water or copper carbonate hydroxide, so he was studying this stuff, he realized that the ratio of the elements in the compound is always the same. It never changes. the chemical formula for water? Like the letters? H2O, yes, you do know. H2O. So for example, so again, he did experiments with other compounds, but water is sometimes simpler to illustrate. If I take a sample of water and I analyze how much of each element is in it, if I remember correctly, 1/9 of the mass is hydrogen atoms, and 8/9 of the mass is oxygen. These ratios are always true for all water all the time, no matter if I have a little bit of water or a big tank of water. If I were to analyze the mass ratio of how much elements is there, it's consistent, it never changes. Okay? This might seem obvious because we already know about atoms, but based on experiments around that time, there were other people that thought otherwise, that, well, sometimes you can use different amounts of hydrogen and oxygen and it still makes water. Okay, but he was able to show that there are definite proportions. If I take this compound here, the amount of mass of the compound that is, or the percentage, you can think of it as percentages, that's copper versus carbon versus oxygen and hydrogen, is the same, no matter if I get some from the dirt and analyze it, or if I make it myself, it's the same compound, it's a definite proportion, it doesn't change. This is where we start to get in the idea that evidence that atoms actually exist. If atoms actually exist, that idea is consistent with this observation. That the atoms are just, they have their mass, and then when you combine them in a certain way, the percentage of the mass for the compound is the same. Okay, so a lot of different proportions, okay? Similar common view at the time, ratio. Okay, I kind of already said this. Okay. So at the time, this was controversial. Okay. Similarly, we have John Dalton, who figured out a similar thing. So we have the law of definite proportions. Now we have the law of multiple proportions. Note-taking tip: these little intro things you don't need to write down. Okay, so I'm not going to test you on this stuff. Okay, just the name and like what they're famous for. It's good. You do not need to know their dates. I'm not going to test you on that. Okay, I'm just giving you an idea. What was happening in the late 1700s in the United States? We became a country. Yeah, when he was like 10 years old, we were like, yeah, we're a thing now. Okay, so the law of multiple proportions is similar to what we just saw. The law of multiple proportions says that if elements form multiple compounds, then the ratios of those elements is always a whole number ratio. I'll give you an example to explain what this means. This is very strong evidence that atoms actually are a thing. Okay, this is significant because this is very consistent with the idea that atoms actually exist. So it's kind of backwards how this works. We kind of assumed atoms exist, and then all the evidence we find is consistent with that. So we just go with it. So maybe not the best way to go about it, but since you can't see atoms, and we still can't see atoms today, it's the best we can do. We kind of assume it's true and then do experiments to try to prove it wrong. And over the last 200-300 years, it hasn't been proven wrong, so we're still going with that idea, and that's why we're learning it in high school. Okay, so check this out. So let me give you an example. Let's say I have 100 grams of carbon. Okay? Carbon can react with oxygen to make a compound. In fact, it can react with oxygen to make different types of compounds. So there's one type of compound where if I have 100 grams of carbon, it could react with 133 grams of oxygen. Okay, and it can make some compound. So all of this reacts with all of that, and I get some carbon oxide compound. okay? But there's another ratio that's possible. Carbon could also react with oxygen. It could react with that much oxygen, where all of this reacts with all of that and makes a different carbon oxide compound. And so the idea here is that what if I took a ratio of these two numbers? What does that equal if I simplified it? Can you see that in your head? Is it 2 to 1? Is the top just double the bottom? Yeah, it's 2 to 1 ratio. Is that a whole number ratio? Yes. And so the idea here is, I wonder if this situation, if I were to simplify the ratio, if I had one carbon atom, maybe in this situation it's reacting with one oxygen. And then if I simplified this situation, maybe my one carbon is reacting with 2 oxygens. Any guesses what this compound would be? Carbon 2 oxides, carbon dioxide. Is that a thing? That is a thing. That's a gas. We're breathing it out right now. Any guesses what this might be called? Carbon monoxide? Ah, okay. So the idea here is that by looking at the ratio of these masses and then simplifying the ratio, it kind of leads us to the idea that at the atomic scale, we have individual atoms that are reacting. And then if I just have this and then just like multiply it by bazillions of molecules, that's where I get these masses. But it's interesting that the ratio is always a whole number, which suggests that there are little units of matter that have a fixed mass, and then when they react, the ratio of carbon to oxygen or carbon to oxygen is a consistent ratio. And I never have a situation where I have carbon with like 1.5 of an oxygen. Like I never get that ratio. I only get whole number ratios, which suggests that the particles we're dealing with are uncuttable units that combine in certain ratios, okay? So the law of multiple proportions combined with the law of definite proportions from before is very strong evidence that atoms actually exist, okay? So do I have another thing here? No. I would make a note that Dalton is the first person who has strong experimental evidence that atoms exist. Prior to Dalton, it was mostly assumed. Pretty sure atoms exist, it just logically makes sense, but we really can't prove it. This is where we begin to have evidence. I have scientific evidence that demonstrates it. Okay, maybe it doesn't prove it, because that's kind of a strong word, but it's very consistent with that idea. Okay, so Dalton is where that starts to shift. Cool? Okay, moving on. Just cruising right through history here. So, because of this, we have a theory of atoms, okay, atomic theory. Okay, Dalton's atomic theory. These are actually what his notes looked like. Okay, so obviously he didn't look at atoms, but he came up with some models to kind of represent that. Okay, these are some of his elements. Notice that they're little hard spheres. Okay, so he imagined that atoms were just like little spheres that you can't cut them and they are what they are. And to represent the different elements, he kind of gave them a different pattern. And then he could show, or he's trying to predict the ratios of how they combine. So, I don't know, one of these might be water. This is hydrogen, and number 8 is oxygen. Do you have water up here? Maybe that one? Although, yeah, I don't know. Okay, but he's trying to figure out how these things are combining. These are what his notes actually looked like. Okay, so his theory is this. All elements are made of atoms. Makes sense, but that's where we're starting. There's 5 things here. Okay. The other thing that he was realizing is that if it's the same element, then the atoms must be identical. And again, he has evidence for this. So all hydrogen atoms are the same. They have the same size and the same mass. That's what the evidence seems to show. Okay, and if you're a different element, then you have a different size and a different mass. Okay, so we're still on this idea that atoms can be subdivided or destroyed. They're just rearranged, okay? Kind of the law of conservation there. They combine in whole number ratios, form compounds, so that's our definite So definite proportions right there from Proust. And then reactions are just rearranged. Okay, so he's kind of bringing together all of this evidence from lots of different sources to come up with a theory that explains all of the evidence. This is his list of ideas that explains all of the evidence from multiple scientists. Remember we talked about that theories need evidence to support them? Okay, that's where this comes from. He didn't just come up with this just because he thinks it's true. He has evidence from Lavoisier and Proust and himself and other people who have worked on this, and all of it seems to conclude with this stuff. And the reason I'm bothering to show you this whole list is because most of this is still valid today. For the most part, this has not been contradicted even from like 100+ years ago. Okay, so number 3 might be a little questionable nowadays, but for the most part, this is basically how it works. It's amazing you can figure all this out just by measuring mass and doing experiments. There's no microscopes or anything. You can't see atoms, but you can figure it out deductively. It's kind of cool. We okay with this? Can I move on? Okay. Okay, now things get interesting, okay? So, there are 5, I think there are 5 models of an atom that I would like you to know. I didn't put it on the slide, but I'll just make a note. Okay, so the first one, so what we had so far up to this point is called the solid sphere model. Solid sphere. Okay, so that's just the idea that atoms are a solid sphere. You can't cut them. There are no subatomic particles, right? We've not talked about electrons, protons, neutrons, none of that. We don't know about any of that. So this is our starting model. Okay, and we're gonna associate that with Dalton, John Dalton. Okay, solid sphere model. Okay, so we'll just make a side note of that. Now things get interesting. Okay, so now we're going to staying in Britain. I think this guy's a cool name, J.J. Thomson. I think that's kind of a cool name. Okay, he's a physicist. And he studied a lot of things, but the thing we care about for right now is that he studied cathode rays, which is actually what TVs used to have inside of them before they got flat screen. Anyone know what cathode rays are? You guys heard of this? Cathode ray tube that come up in a science class ever? Maybe. Sometimes it depends on the teacher if they bring it up. Cathode rays. Basic, well, do I have it up here? I don't have a picture of a cathode ray, but you basically have a metal source and you can basically electrify it and it shoots out a beam of particles. And what he realized is that this beam of particles has an electric charge. And all these different elements will cause the same particle. Iron, platinum, other metals, they all produce the exact same beam of particles. And the particles have an electric charge. They're electric particles. That's kind of weird. The charge is negative, and all the particles are identical regardless of what atom or element they come from. They have the same mass, and they're all negatively charged. That's kind of weird. So the idea here is, well, if I can get these particles from any element, then these particles must be inside every atom. Must be fundamental to all atoms. What do you think is a good name for an electric particle? Electron, there you go. He did not name them electrons, other scientists named it. But if you have an electric particle, it makes sense to just call it an electron. So J.J. Thomson is credited with discovering that electrons exist. So holy cow, atoms aren't just these solid spheres, now there's particles inside of them. This is wild. It's getting smaller. So now we have to go back to the drawing board, almost literally. We have to redraw this. So now our model has to include electrons somehow. Okay, so the electrons are probably inside the atom, makes sense, right? Because they're coming from the atom, so they're probably inside of it. Okay? Obviously, the atom isn't just made of pure electrons, because that would mean everything in the universe has a negative charge. And if everything's not negative, there must be something positive to cancel it out. So let's try to piece all this together. Let's say that the atom has electrons inside, but then the rest of the atom is positively charged so that it cancels out, because we know that not all matter is electrically charged. There's positive and negative. So let's redraw our atom to include all of this new information. What should I call this model? It's on the slide. Plum pudding? It's probably the most British name I've ever heard. I've never had plum pudding, but apparently it looks like that. So, it's this dessert, and there's like little fruits in it. I don't know if it's always plums or berries or something. But it's just named after a dessert. So there you go. Plum pudding model. Okay, so the idea here is that the atom is this kind of positively charged ball, but it has electrons floating around inside of it. Okay, so that's our plum pudding model. So that's the second model, significant model of an atom that we need to know about. Okay, so we've got plum pudding. So we've got electrons floating around in a positive space. Positive space, just like this classroom. Bad job. Okay. Moving. Cool with that? Okay. It gets more interesting. Okay. So now we're going to continue. We're still in England. Ernest Rutherford, widely regarded as the father of modern physics. He's from New Zealand, but he worked in Britain. This is a time in history when radioactivity, radiation, was recently discovered, and so people are studying it. What's radiation? What is it made of? What can you do with it? How does it affect atoms? And people started to realize, you can actually use radioactive beams to study atoms, because the way that those beams behave will tell us about atoms. And so that's what he was interested in. Okay, so he was using nuclear radiation, specifically alpha particles. That's a type of radiation. Okay, and he wanted to see if he could use that radiation to study the structure of atoms and learn something about them. Okay. Side note: alpha particles is a particle that has 2 protons and 2 neutrons. And it's just kind of a side note. Which actually is probably a bad way to say it, because he didn't even know this. We know this now, but he didn't even know this. So. Just for our own knowledge. So if I were to think of an alpha particle as an element, what element would it be? Say what, Tate? Yeah, it's a helium nucleus, right? It doesn't have the electrons, it's just like the middle part. You like shoot a beam of them, those are alpha particles. Okay? So he did a really interesting experiment, okay? So I want to study atoms using this alpha radiation, okay? So what we're going to do is we're going to set up a little experiment here, okay? This is called the gold foil experiment, one of the most famous experiments of all time, okay? So I've got my radiation source, and I'm going to shoot alpha particles at a really thin layer of atoms. If you want a really thin layer of atoms, you need a material that's really malleable that you can smush really, really thin. A really good option for that is gold. Gold, you guys hold a gold leaf. It's like super papery thin. It's like tissue paper, but it's metal. You know, people put it on food. You ever seen like gold donuts and stuff? Yeah, it's really weird. It's like really thin foil. But if you want a really thin layer of atoms, gold is a good option. So he wasn't using gold just because he thought he was cool or trying to waste money or anything. It's like, no, I need a thin layer of atoms. And we're going to shoot this beam of alpha particles at these atoms, and then based on how the beam deflects, we should be able to deduce something about the structure of an atom. Okay? Okay, basically said all that. Okay, according to the plum pudding model, we have a very jelly-like atom. There's electrons in there. There's a positive charge that's distributed over a pretty wide space. The negative charge is pretty small. The alpha particles should just go right through, okay? A macroscopic version of this is like we're shooting bullets at jello. Okay, so you've got a big blob of jello. If you shoot a bullet at it, I would expect it to go right through. That's just me, okay? Based on what we understand about alpha particles and atoms up to this point. But something very different happens, and it's quite surprising, okay? Most of the particles did pass through, okay? So they go through the foil, they end up on the other side of the detector, okay? He's got a detector all the way around to see where the radiation ends up. Some of it is deflected, which is expected because this is charged, and right, we know that like charges repel, so it's going to deflect a little bit because the electric charges are going to interact. But something super surprising happens. Some of the alpha particles are deflected greater than 90 degrees, and some of them bounce straight back at the detector. This is totally against what we would have predicted based on what we understand of atoms. The plum pudding model does not predict this kind of behavior. Okay, and he even said that. Okay, this is about as credible if you had fired a 15-inch shell, okay, a giant like cannon bullet at tissue paper and it bounced back and hit you. Okay, this does not make any sense. This is totally unpredicted. Okay, I'm going to glaze over a bunch of math. Okay, he's a physicist. There was a lot of angles and electric charge and math that went into this. I'm just going to skip to the end here. Okay, clearly our understanding of the atom is not accurate if atoms are causing alpha particles to bounce off like that. That doesn't make any sense. Okay, so we need a new model of the atom. We need to account for this. Okay, and so the conclusion here is that atoms are more like this. Okay, atoms have a small, dense, positively charged core. And I'm sure we're all familiar with the name for this core, is the nucleus. Okay, this is the only thing that explains how an alpha particle could bounce up, because an alpha particle has a positive charge. So if an alpha particle were to come flying in at something else that's positively charged and really dense, that would make sense why that would bounce off, right? Because positive repels positive, yes? Okay, and if this is really dense and heavy, then it has the ability to totally deflect the alpha particle. Okay, but remember, not all of the alpha particles bounced off, so it's not like the entire atom is just this big, bulky thing. It's only part of it is bulky. Okay, so the majority of the atom is empty space. Most of the alpha particles just flew past it. Okay, and the electrons must be in the space around the nucleus. Okay, so he didn't have a very specific idea of where the electrons are, how they move, but he concluded that they must be outside the nucleus. They're somewhere on the periphery. Okay, and then it was subsequent experiments that we realized, oh, this nucleus is actually made of particles. Okay, and that's where we get protons. Okay, we're going to call this the nuclear model. Okay. Okay, and I'm going to draw this a little different than the slide. I'm going to actually put protons on my model. Okay, and I'm just going to have electrons chilling out over here. They're just kind of floating around. So two things I want you to, or three things. Gold foil experiment, okay, that's Rutherford. Okay, he did not do the experiment by himself. He actually had people that helped, but he gets most of the credit, so that's how that works, I guess. Gold foil experiment, nucleus, protons. Okay, that's all part of Rutherford's work. Good? Can I move on? I'm just gonna crank through this whole thing. Sorry this whole lesson is like slides, but we don't do this every day. Okay, and then quick side note, James Chadwick, probably the most British name you could ever think of. James Chadwick. Probably ate lots of plum pudding. He also found that all atoms could emit a beam of neutrally charged particles. Okay, and these particles come from the nucleus, and all elements that he observed could emit these particles. What should I call a particle that comes from an atom that has a neutral charge? Neutron! This is the discovery of neutrons. James Chadwick is credited with discovering neutrons. So, kind of a modified nuclear model. Right? I'm not going to make a whole nother one to the list, but now we have neutrons in the nucleus. Okay, so Chadwick, neutron. That's connected in our brain. Okay, I got two more people. You hang with me for two more people? I guess you have to anyway. Okay, so now we're moving in. Now we're getting into the heart of the 20th century here. Wild guess where he's from? Say what? Did you say America? Good guess. Northern Europe. His name is Niels Bohr. I don't know if that helps or not. He's Danish. Daniel doesn't like Denmark. Okay, so this is where I start to like grossly oversimplify his work and all of the stuff he was putting together. But I don't want to get too deep into the weeds about this, okay? So what I'll just mention for now is that electrons only emit certain colors of light, regardless of the light that you shine onto them. Okay, and so what this might look like is if you have hydrogen and you shine light to it and you give energy to the electrons, you can shine high energy light, low energy light, this color light, that color light. You can do all kinds of things to it, but the only light you get out of the hydrogen atom are these four colors. You get violet, kind of a blue, aqua teal, and then red. You get four colors from this element, and then depending if you had a different element, you might get different colors, but you only get certain colors from certain elements. And we know that the color is coming from the electrons. The electrons are vibrating, and then they spit out that energy as light, but they only spit out certain colors, which is weird. It's like, why can't we get these electrons to do other things? These electrons seem very restricted in how they're able to move. Movement and energy of electrons is restricted. They can only exist at certain energy levels. Interesting. So now instead of electrons just moving around willy-nilly and doing whatever they want, now they can only do certain things. And this is just some evidence that suggests that. Electrons can only do certain things. They can't just be anywhere or do whatever they want. They have to have certain energy and only move in certain ways. Okay, enter the Bohr model. Okay, so we still have a nucleus. This is kind of an oversimplified nucleus, right? Because there should be protons and neutrons in there. Okay, from Bohr we get the Bohr model, so that's probably the easiest one to remember. Who does that? Okay, and the idea here is that I have my nucleus. Okay, but now the electrons are restricted to only certain movements. Okay, and the way we're going to represent this is by putting them on little orbits, okay, kind of like planets. And these orbits represent energy levels. Okay, so this n equals 1, n equals 2, n equals 3, those are energy levels. 1, 2, 3. Okay, and electrons can only exist on certain energy levels. Okay, they can change energy levels. So here what this is showing is an electron was here on energy level 3 and it kind of jumps down to number 2, spits out some energy, so this is light coming out. So they can change energy levels, and atoms can emit colors, but they are restricted to certain energy levels. You cannot remain in between them. You're either here or there, or here or there. You can't be anywhere, and you can't move any way you want. There's a very specific pattern to how this works. Okay. Now this atom only shows 3 energy levels, but for our periodic table we could go up to 7, and we'll talk about this in much more detail in the next chapter. But there are 7 energy levels for elements on the periodic table. Okay. Also notice I said elements on the periodic table in their lowest energy state. Technically there's an infinite number of energy levels. If you put in energy into the electron, you can make it jump up a zillion energy levels until it just leaves the atom altogether and goes somewhere else. But when it's in its low energy, like resting state, the electrons are kind of stacked on 7 energy levels. So that's what I'm trying to say. So we could draw this like going out even more. Okay, so this is where we get the idea of valence electrons. Okay, so now we're realizing, certain electrons participate in making chemical bonds, and others just stay toward the core of the atom. Okay, so valence electrons are exchanged. They can make chemical bonds, or when we make ions, remember we talked about losing or gaining electrons to make ions. Those electrons that are trading partners or moving around, going from one atom to the other atom, those are the valence electrons. They're on the outskirts, so it makes sense that they're the easiest ones that can leave or join to make an atom have a positive charge or a negative charge. Okay, so those are the valence electrons. Okay, so this is our Bohr model. Cool with this? So we have 4 models so far. Solid sphere, plum pudding, nuclear model, Bohr model. Okay, we got 1 left. Ready? Okay. Last person, Erwin Schrödinger. He was Austrian. Or Austrian-Irish, I guess. Okay, now we're getting into quantum mechanics. Okay, this is where I'm going to tell you the super oversimplified version of this because I have not even studied the full extent of this. I would have to be like a physics major to fully take these classes, and we didn't get into that completely. but I can give you a simple version. Okay, so in the first half, the 1920s, 1910s, 1930s, okay, we get into this idea of wave mechanics where we know about radiation, we know about light, we're studying this, and so light is a wave, and so scientists are studying waves, they're coming up with equations that describe how waves work, how much energy does a wave have, how fast does it move, what's its frequency, all of that stuff, okay? But strangely enough, this is where it gets weird. We thought electrons were particles, right? Tiny little specks. But now it seems like electrons could be imagined as waves. Standing wave. So a wave in one spot that's just vibrating. So it's not a particle, or maybe it is, but it also, the equations that describe how waves work now apply to electrons. So now electrons might be waves, not particles. It's kind of mind-bending. Okay, equations for waves could be used to understand and predict the behavior of electrons. Hey, I just said that. Okay, so I'm leading into this idea. Okay, so this is where he came up. This is his big contribution, is coming up with an equation that can describe how an electron behaves. And you have to start simple. So let's think of an atom that has one electron and one proton. So that's hydrogen, right? Very simple. Let's start simple and see if we can come up with an equation that describes how an electron wave would behave. Okay, so we're imagining electrons now to be something like this. It's not a particle moving around, it's a wave on the atom vibrating a certain way. What energy does it have? What momentum does it have? How does it move? Things like this. Okay, so this is kind of like a visualization of like electron is no longer a dot, it's a wave now. Okay, it's kind of weird. Okay, now just to give you a sense of how crazy this math is, this is his equation. That's the simplified version. You can expand it out to include more information. It looks a little something, oop, my phone's trying to die. Looks a little something like that. Okay, so this is the expanded form of this equation. We will not be doing this math in this class. Okay, but I'm just giving you a sense of like the level of mathematics that goes into this is like upper level college physics is where you start to get into this stuff. Okay. You remember on the Bohr model it had like n equals 1, n equals 2, the energy levels a few slides ago. Okay. In, okay, it's in there. There's a little n right there. Okay. L, stuff like that. So we're going to talk about some of the numbers in this equation, but we're not going to use this equation. Okay. But I'm just giving you a sense of what this looks like. It's pretty gnarly stuff. Okay, but we're not going to worry about it. Okay, but this idea that electrons could be waves actually works. You can use these equations and it makes sense. So, kind of weird. So now the Bohr model is not totally accurate because little dots going around in circles doesn't make sense. Also, this is like two-dimensional. We need a three-dimensional model, so this also makes it three-dimensional too. Okay, so let me just skip to the end. We have a cloud model now. Okay, so now we don't know exactly how the electrons move. This equation can tell us the energy of the electron, it can tell us its momentum, maybe where it spends most of its time, but it can't show us exactly where it is, so that's where we get the cloud model. Okay, and I will just pause here. The bell's about to ring. Okay, but we've already talked about this. The cloud is a three-dimensional space. Okay, it's not a container that traps electrons. It's not like they're bouncing around in this bubble. It's just showing where they spend most of their time. Okay, and the movement of electrons cannot be precisely tracked. They move in unpredictable paths in this three-dimensional space. Okay, and so this is the most accurate model of an atom that we have so far. That was like perfect timing. So that's our fifth model, the cloud model. Cool. Thanks, guys. I will see you tomorrow. Yeah. See you, Daniel. Wow, my keys aren't working.
Oh wait, I forgot.
Well, turn. Oh, wait, there it goes. Yeah, it definitely was RIT. Sorry, I wasn't trying.
Thank you.
Yep.